again. The topic rolling is not yet complete. Few more things are remaining. These are mechanical energy of rolling and its conservation, rolling on an inclined plane, rolling on movable planks. So let us see how these situations are solved when it appears in a numerical problem. This topic is very important for your examination point of view also. Every year at least 2 questions you will get from the chapter rotation. So let's get started. In the last session, I had discussed about the strategies how numerical has to be solved in case of rolling. So let us start first with a question. A uniform round object of mass m, radius r and moment of inertia about its center of mass, that is given ICM, has a light thin string wrapped several times around its circumference. The free end of string is attached to the ceiling. Let us draw the situation. It is the string which is wrapped on a round object. So it has to be like this. Now what the forces are here? It has to be tension, mg at the center of object, and then of course its radius is given, mass is given. Now if I write equation for translatory motion, that will give mg minus t, because as the string is unwrapping, the object will come down. So it has to be mg minus t is equal to ma. This is our equation number 1. Now if I write for rotation, then it has to be, as you can see, mg cannot produce any torque. It is passing through center of mass itself. So equation will be tr is equal to ICM alpha. This is equation number 2. One more condition we can write, because there is no slipping associated. So we can write always A to be equal to alpha r. This is our equation number 3. If I solve these equations, that will give mg minus ICM A upon r square is equal to ma. From here we got A to be equal to mg upon m taken common 1 plus ICM by mr square, which can be written as, m will get cancelled, so it can be written as g upon, and then this is 1 plus ICM upon mr square, which is our first part, acceleration of center of mass. Next we have to calculate value of tension. Now from here itself, if I substitute this value for expression for tension, it will give ICM A upon r square. So on substituting value of A, it will be ICM G upon r square 1 plus ICM upon mr square, which is our second part, tension in the string. Let's see one more question. A disk of mass m has a light thin string wrapped several times around its circumference. The free end of string is attached to the ceiling and the disk is released from rest. We have to calculate acceleration of disk and tension in the string. This is again similar to the first one, so directly we can draw FBD for the situation. Forces has to be tension here and then mg. Let us write F is equal to ma. That will give mg minus t is equal to macm, which is equation number 1. The next equation has to be for rotation. So that will be tr, only tension has an effective torque. So tr has to be equal to, now it is given a disk, and we know that for disk, moment of inertia about center of mass can be written as mr square by 2. So this is mr square by 2 into alpha, which is our equation number 2. One more equation we can write, that is ACM is equal to alpha r. On solving these three equations, we can write final answers to be A will be equal to 2g upon 3 and T is equal to mg/3. As you can see, we have followed all the steps I had discussed in last session about solving a numerical problem related to rolling. The first was drawing an FPD, and the next writing F is equal to ma, then writing torque is equal to I alpha, and at the end solving all the equations. So we followed the steps and got our answers. I hope you understood the steps clearly. The next kind of rolling I am going to consider, that is rolling on an inclined plane. So if we consider an inclined plane which has some inclination given theta, and an object is here which can roll on the incline. Now let us consider this round body is released from rest on the inclined plane, which here I am going to consider as rough. It is a rough inclined plane, so that it can roll down without slipping, because if surface is not rough, then it will start rolling with slipping. So if it has to be rolling without slipping, surface has to be rough here in the given situation. Now what forces will be there? It has to be weight and then normal. Let us consider the center of this round object is coming down with acceleration a. Now what equations we can write? Of course, one friction also will be there, one friction force. Let that be F. Now if I write F is equal to ma along the incline, that will give mg sine theta minus Fr, that is the friction here, is equal to ma. Here a is acceleration of center of mass. Now do remember that while writing F is equal to ma, always we have to consider our bodies like a particle mass. So whatever we write the acceleration, it has to be for the acceleration of center of mass. So this is our equation number 1. The next equation we can write for torque. Now if I write torque about center, then what torque will be effective? It has to be only for friction, because mg is passing through center, n also is passing through center. So only friction can produce a torque about center of mass. So it can be said that friction is needed for rolling in the situation shown where no other external force is acting. And I am writing torque for the friction, that will be Fr multiplied with, if radius is written as r, so then Fr into r has to be equal to I alpha. This is our equation number 2. One more condition we can write, A is equal to alpha r, considering that there is no slipping. Already I had said at the start itself that we are considering the case of rolling without slipping. Now if I solve these three equations, I will get mg sine theta minus Ia upon r square to be equal to ma. And from here a can be written as g sine theta upon 1 plus I by mr square. So this is our result. You can see it is a general result because I haven't written the value of I. It can have value mr square by 2 if it is a disk, mr square if it is a ring, 2 by 5 mr square if it is a solid sphere, 2 by 3 mr square if it is a hollow sphere, and so on. So based on the situation given in problem, we can put value of I. But again I am saying there is no need to memorize the result. Just you must be able to write the basic equations. The equations always has to be first for F is equal to ma, and the second torque is equal to I alpha, and the third condition that comes from rolling without slipping. If you understand these 3 points, you can solve any kind of question related to this topic. Let us now consider one numerical based on this. A solid sphere is projected along an inclined plane according to diagram. Diagram you can see here. If coefficient of friction is mu 0.5 given, I am writing here the value mu is equal to 0.5 and radius r, then find time when linear velocity becomes 0 and angular velocity at that instant. It is the instant when linear velocity has become 0. Okay, let us start solving this question. First, I am drawing FBD for this sphere. If I draw all the forces, this is mg, normal here. Now, as you can see, velocity of lowermost point is not 0, and so it is not the case of pure rolling. And friction here has to be kinetic friction. Now, since velocity of lowermost point is in forward direction, then friction has to act in backward direction. So, if I write friction to be in backward direction, that will be here, which is obvious from the kind of rolling which is shown here. This is anti-clockwise. So if you see at this contact point, the contact point will move towards right. So friction has to be towards left. So let us first write F is equal to ma, what forces are acting along the incline. The first equation will be mg sin theta plus, here directly Fr can be written as mu n because this is a kinetic friction, so it has a fixed value. I am writing this mu mg cos theta, and this should be equal to ma. From here we got a to be equal to g sin theta plus mu cos theta. And if I substitute all the numerical values, this will come out to be 1.5 g upon root 2. Now let us write torque. So torque only we can write for friction because mg and n both are passing through center of mass. So if I write torque of friction, that will be equal to, of course, mu mg cos theta into r, and that has to be equal to I alpha. I, since it is a solid sphere, should be equal to 2 by 5 mr square alpha. From here we can get value of alpha, that will be equal to 1.25 g upon root 2r. If you substitute all the values, you will get this result. Now one more thing we have to write, because this is not a pure rolling. So here we cannot write a is equal to alpha r. Then for translatory motion we can write v dashed to be equal to v minus at, because as it is moving in upward direction and net acceleration is in downward direction, so it is a kind of retardation here. I am writing final velocity to be equal to initial velocity minus it, or it can be written as v, as it is shown here, is r omega. So this is r omega minus it. Now we have to consider the case when linear velocity has become 0. So just substitute this value 0 here. 0 is equal to r omega minus at. What is value of t then? T is equal to r omega upon a, and on putting the numerical values, it will come out to be root 2 upon 1.5 omega r upon g. This is the time when linear velocity has become 0. In next, it is asking for angular velocity at that instant. So again, let's apply the kinematical relation for angular velocity, that can be written as omega is equal to initial omega minus alpha t. So it will give omega minus alpha, already we have the value. T also we have calculated, so it will come out to be 1.25 omega upon 1.5, and the final answer will be omega by 6. So this is the angular velocity at the instant when linear velocity has become 0. With this, we solved both the parts of the question. Let's move further now. The next I am going to consider is rolling on horizontal surface without friction. This time friction, if it is not there, how rolling can take place? First we have to think for it. Now if rolling is taking place and still friction is not there, the very important thing is that an external force should be applied on the system. Then only the case is possible. So let us discuss this now. It is an object which has to roll on the surface, and for this rolling to start, an external force is applied like this. Here for simplicity, mathematical simplicity, I am considering our object to be that of a ring of mass m and radius r. Its mass is m. Now if this force F is applied on top of the ring, then let us first write if friction force is there. I am considering first that friction force is acting, and then we can see later that how this friction becomes zero. So let us consider that friction is acting on the ring. Of course, it has to be at this point where the ring is in contact with the surface. Now as friction has to be static because this is pure rolling, so it can be assumed in this direction, forward direction. So this be the direction of friction. One normal has to be applied here from the surface. Now if I write equation for translation, that will be F plus F to be equal to mass into acceleration of center of mass. This is our equation number 1. And for torque about center of mass, we have to write F minus F to be equal to, this is a ring, so I am writing mr square as I and then alpha. This is our equation number 2. If it is a pure rolling, always we can write ACM to be equal to alpha r. Now if you substitute this value here, you will get F to be equal to 0. And now we can say that if it is a pure rolling and an external force is there to provide the torque, then friction will be absent if it is a pure rolling, because this point of contact will be at rest with respect to the surface. So no friction will be there, which is verified from the result we got. Now let us do one question based on this concept as well. A uniform round body of radius r and mass m and its moment of inertia about center of mass O is ICM. These things are given. Radius is there, mass is there, and moment of inertia is also given. A force F is applied, as you can see in the diagram, at a height h above the center of the round body. Find the height h at which force should be applied so that it rolls without friction. As you can see here, we have to consider the condition when friction is not present. So let us start with writing F is equal to ma. Always we have to write this equation as the first equation. So let us write F is equal to, because all other forces, one will be mg, one will be normal, only horizontal force given is F. So F should be equal to MACM. This is our equation number 1. Now if I write torque about O, what torque will be effective? Again it has to be only of torque that is provided by the force F. So if I write now torque, which is Fh, because the force is acting at a perpendicular distance h from the center of mass. So Fh has to be equal to ICM alpha. This is our equation number 2. Now if it is a pure rolling which is given here, so ACM has to be equal to alpha r, which is equation number 3. On solving all these equations, we will get H to be equal to ICM upon MR. This question has come in different form so many times in your exams, both in JEE and in NEET. So it is a very popular question where you have to calculate the height h so that rolling can take place without presence of friction. And depending on the object which is rolling, we can substitute value of ICM and then get different result for different heights needed for the force to be applied. Let us see one more small subtopic, that is rolling on a moving plank. Now if rolling is not a static surface, till now we had considered rolling on a fixed surface, and this time if it is not fixed, what will be the conditions involved and how it will change the scenario while solving a numerical. So let us consider that one plank is there which is moving with some speed, let that be Vp, because I have written for the Planck, so it is denoted by Vp. On this Planck, one object is put for which center of mass has velocity v0 and it is rolling with angular velocity omega. Center I am writing by O. Now if it is a pure rolling, then we have to consider that the contact point should be having the same speed, because it is the first criteria for pure rolling that relative velocity of contact point should be 0. So if relative velocity is 0, we have to write the velocity of this point, whether it is for the Planck or for the object which is rolling. These two velocities has to be same because they are in contact with each other and relative velocity should be 0. From here we can write for the round object, velocity at this point should be equal to v0 minus omega r. As you can see, velocity of center of mass is in forward direction and due to rotation, the point will get an omega r. I am showing it separately here. Center of mass is moving with v0. So here this point with center of mass will move with the same velocity v0 in forward direction, and then due to its rotation about center of mass, one omega r term will come here. So if I write velocity of this point, that should be equal to v0 minus omega r, and as relative velocity with the Planck has to be 0, so this should be equal to Vp, because the point which is in contact with the round object has velocity Vp at this location. So it has to be equal to Vp. Similarly, we can write for acceleration as well. A0 minus alpha r should be equal to Ap if there is some acceleration also for the Planck. And if it is a forward slipping, these two conditions we had got for pure rolling when no slipping is involved. So these conditions are for pure rolling. Next, if we write for forward slipping, because we had already discussed that 3 types of rolling can be there: pure rolling, and among impure it can be forward slipping or backward slipping. So if it is forward slipping, then this v0 minus omega r, it is forward slipping, do remember, so this has to be more than Vp. It is moving against the contact surface in forward direction. Similarly, we can write for acceleration, A0 minus alpha r should be greater than Ap. These two are the conditions for forward slipping. The next I am going to consider backward slipping. And what conditions has to be there? For backward slipping, it should be v0 minus omega r less than Vp, and the similar for acceleration, A0 minus alpha r less than Ap. So here all the conditions I have written for velocity and acceleration if the rolling is pure or impure. And now depending on the situation given in your question, you can consider any relation among these all shown here. So let us consider one example now. A sphere of radius r rolls without slipping between 2 Plancks as shown in figure. Find speed of center of sphere and next angular velocity of the sphere. As you can see, both the Plancks are moving with velocities v1 and v2 in forward direction, and center of this sphere is moving forward with velocity v. So if there is no slipping, because it is given there in the question that no slipping is taking place. So if it is no slipping at this point, relative velocity should be 0. Now what is the velocity at this contact point? If it is for the Planck, that is equal to v1. But if it is for the point on sphere which is in contact with the Planck, this should be equal to v plus omega r. So we got this first equation. Just you have to consider that relative velocity should be 0 if there is no slipping involved. Now let us consider this point also, because here also the sphere is in contact with the Planck, and this time Planck has having velocity v2 What about the contact point? Here, this must be having velocity v minus omega r. As you can see from the given situation, omega is in this direction. So if I consider this point, omega r has to be here, v in forward direction, but for uppermost point, both v and omega are in the same direction. So first I have added v plus omega r, and for next point, which is the bottom point, I have to write v minus omega r, and that should be equal to v2 because the Planck is having velocity v2 here. This is our equation number 2. On solving these two equations, we will get v to be equal to v1 plus v2 by 2 and omega to be equal to v1 minus v2 by 2r. So with this, we got speed of center of sphere as well as angular velocity of the sphere. Do remember, only one thing you have to keep in mind, that if it is a pure rolling, relative velocity of contact point should be 0. So just write the velocity of Planck and then write the velocity of contact point for the rolling object. Equate these two values and you will get your result. With this, today's session is complete. In next session, I am going to discuss energy related to rolling. So let's wait for the coming session. Till then, keep practicing and be safe. Goodbye.